Okay, this lesson is going to start looking at planes and the equations of them. Obviously, if we're dealing with planes, we're dealing in 3 dimensions. We talked about at the beginning of this course, um, when we started looking at 3 dimensions, that you can think of our classroom as the coordinate planes, and the front wall would be a 3 dimensional plane, a vertical one. The floor would be a 3 dimensional plane, a horizontal one, and the left and right walls could be planes. And those are easy planes because they're vertical or horizontal, but planes don't have to be that way. They can travel through 3 dimensions at once, kind of like a line. So if we were to think about a line traveling, I don't know, 3 dimensionally like this, the plane version of that would be, well, it would extend horizontally and vertically in all 3 dimensions at once. And think of a piece of paper on a diagonal. That's really what's happening here. Um, because these are a little bit hard to imagine, we're not going to draw them out so much. We're just going to have to try and picture them in our brains. So it might be helpful to think about like your table, and if I tilted that, or a deck of cards, and you can think about which different ways cards could point. Yeah, but it can be a little bit tricky to visualize at times. To show a parallelogram, to show a plane, we often use a parallelogram. Okay, so thinking about the xy axis, as this was your axes, the idea of a parallelogram comes from, well, if I did this, and that would be a parallelogram on the floor, if you will, and that's where we get the idea of a plane. And we also use the symbol for pi, so our equations are going to be vectors, so pi with a vector symbol over top of it. Define equations. Well, when we did lines, we need to know where we started and what direction we went. Kind of the same idea as a plane, except for planes go in more than one direction at once. So there's some options for making equations. Option one, well, if we know 3 points on our plane, because if we know 3 points, we have a plane that looks like this. With 3 points, we can get a direction and another direction, and we know what this plane has to look like. We could have one known point and two non-collinear vectors. Basically what we just drew, right? 3 points makes one known point and two collinear vectors, non-collinear vectors. We could have two intersecting lines. Well, again, that's what the picture looks like, right? Two intersecting lines. Okay, so the first three things are really combinations of each other. And for option four is we have two parallel and non-coincident vectors. And so if we knew this vector and this vector, they're not coincident, but they both point in the same direction. So we can get an idea of what this plane is going to look like, because they both involve points that are not on top of each other. And as we said, if we know points, we can actually figure out a vector that joins those two things together, and then we can get a description of this plane. When we start making these equations, they're going to kind of similar to what we did before with lines. We're going to have a point, and we're going to have two directions. Together, that's going to make ourselves a vector equation, which basically looks like a line with this extra piece at the end. So we'll have an S and a T now. Parametrically, it looks very similar. We have an X, Y, Z, except we have this extra piece because we have an extra direction at the end. So basically the same idea, is just one more step, if you will. Let's take a look at the first one. We got 3 points. I want to find a vector equation and the parametric equation for the line containing all 3 points. That was one of our options. So first thing we need to do is figure out some directions. We can do that. We can figure out the direction of AB very quickly. AB will be 1, -5, and 3. And I could pick another direction. Let's do AC. I could also have done BC. That's totally fine. AC will be 5, 0, and 1. I got two directions. I also have a couple points. I can have a choice of which ones I want to use. I'm going to use A just because I've used A already for a few things. And my vector equation for this plane would be my point, 2, 5, 1, plus my directions, 1, -5, and 3, and 5, 0, and 1. And again, I could have used A, B, or C here. I could have used A, B, B, C, A, C there, and another one there, as long as they're not the same ones. So lots of choices of how you make this equation. parametrically, I get x equals 2 plus s plus 5t. I get y equals 5 minus 5s, and there's no t's. And I get z equals 1 plus 3s plus t. And obviously your parametric equations depend on your vector equation. So there's some interchangeable options there also. So when you're checking answers in the back of the book, one of the challenges is going to be you not always have the same answer because you have different choices of what you did for your initial part. Try a second one. So the equation of the line, equation of the plane containing a line. What that's telling us is I've got a plane, and on that plane there's this line. And I know for sure that line lies on that plane. Well, the nice thing about a line, just go back to a line for a second. A line is made up of a point, 5, 0, negative 1, plus a direction, right? 3, 2, negative 2. Well, if I have a line, a point in a direction, I'm talking about a plane, well, that's kind of part of the information I need, right? I know my plane has to contain a line, sorry, a point and two directions. I've got one set of information already. Point, a direction. So all I need really is another direction. And I can find a direction because they gave us another point. They said the point 401 is also on there. So I'll call that point A, if you will. And I can give myself a second direction. How can I do that? Well, I've got point B and point A, so I know that A, B would have to be negative 1, 0, and 2. So what do I got now? I've got a point, and you can choose either one. You can use point A, you can use point B. It doesn't make a difference which. I'm going to use point A, let's call it 401, plus I've got a direction. Direction number 1, I can use negative 1, 0, and 2. And direction number 2, I can use 3, 2, negative 2. Now again, I could put those in different orders. I could have used point B here. I could have had a scalar multiple of AB. That would have been fine. That would give me a different, same direction, just a different version of it. Lots of choices. Parametric form. X equals 4 minus S plus 3t. Y equals 2t. And Z equals 1 plus 2S minus 2t. Okay, so there's our two forms. Sometimes we want to know, do points lie on this plane? Are they coplanar, if you remember that word from previous? To do that, we can use our parametric version and solve for our parameters. If our parameters come out to certain values, they'll tell us if points lie on the plane or not. So using the parametric equation in the previous example, determines the point 925 lies on the same plane. So in the previous example, just copy and paste it in here. We had these parameters, and we're going to use those to figure out if 925 is here. How can we do that? Well, 925 is an x, y, and z, right? So we can write down that 9 should equal, if it works, 4 minus s plus 3t. Y, 2, should equal 2t if that works. And z, 5, should equal 1 plus 2s minus 2t if it works. So we've got two variables, we've got more than two equations. We can solve two and check the third. So I'm going to pick the easiest two to solve. And I think the easiest one to solve for sure would be this one, right? Because I can solve that right off the bat, TSP1. If I use that in this one now, 9 minus 4 minus, 9 equals 4 minus s plus 3 times 1. I can solve for s pretty quickly. I can do 9 minus 4 minus 3 equals negative s. So I got 2 is negative s, so s is negative 2. And then I can check. So my check is 5 equals 1 plus 2s, so 2 times negative 2, minus 2t, so 2 times 1. I've got 5 equals 1 minus 4 minus 2. Does 5 equal negative 5? No way. So what does that tell us? It tells us that this point is not on the line. Okay, if it come out to positive 5, obviously it would be on the line. Okay, that's the way you can use that equation. Okay, let's take a look at the next thing. A little problem solving, a little thinking here. So, the plane has this equation, a point in two directions, as its definition. Can we give the equation of two intersecting lines that lie on this plane? Well, what does that mean? Thinking about my plane. I got one line that goes this way, I got another line that goes this way maybe, and they're going to intersect at a point. Well, what do I need to know for those lines? Well, they each have a point on them, probably this one, and they each have directions. I can figure that out by looking at this. I can say line number 1 goes through the point 2, 3, negative 4, and it has a direction called S, 1/3, 2/4, negative 2, 6. Line number 2 also goes through 2, 3, negative 4, but its direction has to be the other part. Yeah, I got myself two lines. Let's say some planes. They give you lots of information. What point do these point lines have in common? Well, obviously that would be the point 2, 3, negative 4. What would a better equation for this plane be? Now, why would they ask for a better equation? Well, if you notice the first direction, fractions. We don't really like working in fractions. We like working in whole numbers. So if we can turn that into whole numbers, that would make our life easier. And we know that we can turn it into whole numbers because we can make a scalar multiple. To pick one, what can we do with that? Well, if I multiply the common denominator of 12, what do I end up with? I'd end up with S times 12 over 3, 24 over 4, negative 24 over 6. So I could write this as 2, 3, negative 4 plus S times 4, 6, negative 4. We need the t part there too. Negative 2, 3, 5. Negative 2, 3, 5. This would be a better, easier version to work with, probably. You could even change that one if you want to. You could say this is the same thing as 2, 3, negative 4 plus S. Those are all multiples of 2, so we could say that. That might be easier to work with than the fractions or even larger numbers. But every single one of these are equivalent to each other because they're the same directions, just different versions of each other. Okay. Part D. What are the parametric values corresponding to the point negative 8, 6, and 15? We need to solve for the parameters, which means we need the parametric equations, which is nice that we now have a nice, easier version to work with. So x equals 2 plus 2s minus 2t. Y equals 3 plus 3s plus 3t. And z is negative 4 minus 2s plus 5t. And we're going to take two of these and solve them at one time, and then check the third. So what do we know? Negative 8, 6, and 15. So negative 8 goes here, 6 goes here, 15 goes here, right? That's the values that we were given, x, y, and z. Then we're going to have to pick two to solve. So to make this a little bit easier, I'll make this negative 10 equals 2s minus 2t. And then this one, I can make that simpler by doing 3 equals 3s plus 3t. And over here, make that easier by doing 19 equals 2s plus 5t. Now I don't have one that stands out obviously as easy to solve like we did the previous question, but I might notice that both of these, the first one and the second one have, first one and third one have some similarities to them. They both have the letter 2s in there, which means I can do elimination. So 2s minus 2t and 2s plus 5t. My s's are the same, so same sign, subtract. Negative 10 minus 19 is negative 29. The s's will cancel each other out. Actually, I just noticed that there's a little mistake in here. Back up here, I was writing this out. I put a plus sign here. It should be a minus sign. So I'll fix that, otherwise I'll throw everything off. Okay, minus sign, minus sign, minus sign. So it isn't same sign subtract, it's actually opposite sign add. Sorry about that. So we're going to add here. Negative 10 plus 19 makes 9. The s's will cancel each other out. Negative 2 plus 5 makes 3t. So t is 3. Picking one of my original equations. And I'm going to pick the second one. I know t is 3. Oops. So I can put 5 times 3. So 19 minus 15 is negative 2s. 4 is negative 2s. Negative 2 is s. So we think t should be 3. I think s should be negative 2. How do I check it? I pick the third one. So I check. 3 should equal 3s plus 3t, where we think s is negative 2 and t is 3, and see what happens. So 3 equals negative 6 plus 9. 3 equals 3. So yes, we have the right answer for our parameters, our parametric values. And there's a lengthy one there. Okay, last part of this. Why would the equation that not represent the same plane, or in fact, any plane? So what do we notice about this? It's got the same point, so that's great news. It's got two directions, and obviously they're different directions than we have. Though this one looks kind of the same, right? The 1, 2, negative 2. But why does this not represent the same one? Well, this direction, let's take a look at that one. That's obviously different than the initial one we were given. And what do we notice, in fact, about these two things? Well, if we call this M1 as 1, 2, negative 2, and M2 is negative 3, negative 6, and 6, you might notice that M2 is actually equal to negative 3 M1s. So that's a problem. You can't define a plane by using collinear vectors. All it's going to tell you is if you have this idea of a plane, you have a line that goes in this way, and then another line right on top of it in the same direction. All that can define for us is a line, basically. Okay, so that does not define a plane if you have collinear vectors. Okay, last one. Determine where the plane intersects the z-axis. So we're thinking three dimensionals. We've got this plane, and we want to know where does this plane intersect the z-axis. Okay, so how can we do this? Well, it's going to intersect the z at a certain point. Call it a dot right there. What point is that? Well, it's going to be 0, nothing on the x, nothing on the y, and some value for c. So I need to be able to solve for that value of c. How can I do that? Well, I have these parameters, and I've got values. I can plug values in for parameters. That's what we've been doing, right? So I can say 0 should equal 6 plus s plus 2t. I can say 0 should equal negative 2 plus 3s plus 2t. And c should equal negative 3 minus t. I don't know what c is. That's what I'm trying to find out, right? So to figure out c, I need to know t. In order to get t, I got to be able to solve for it. So I have to use the other two equations to solve for that t. So how can I do that? Well, I can rearrange these equations. And rearrange this equation. And notice, which is nice, that these two equations are set up for elimination. I'll just rewrite this one underneath here. And our t's have the same value, so I can subtract. 2 minus negative 6 is 8. 3s minus s is 2s, and 2t's will eliminate. So I'll get s is 4. Go back to one of my originals. Let's write down the first one again. So negative 6 equals 4 plus 2t. Negative 10 equals 2t. Negative 5 is t. And now I can find out what c equals. C equals -3 minus t, which is -3 minus -5 minus 5, which is 2. So I know that this intersects the z-axis at the point intersects at 0, 0, 2. And I can do that for any equation, or sorry, any intersection of the axis. I just have to figure out a, 0, 0 for the x-axis. B would be 0, sorry, the y-axis would be 0, b, 0. And we just did the z-axis. Okay, and that takes us to the end of planes.